Ever wondered why the universe, in all its vastness and complexity, seems to repeat patterns both in the macrocosm of galaxies and the microcosm of subatomic particles? Could it be that the universe itself is a fractal, a shape that repeats its pattern at different scales? And if so, how does this idea of a fractal universe fit into our understanding of quantum field theory, the mathematical framework that describes the behavior of subatomic particles? In the 70s and 80s, Mandelbrot proposed a fascinating idea: the universe as a fractal pattern on large scales. This fractal cosmology model is backed by observational data, which shows that the universe is fractal on scales larger than 100 megaparsecs. But while this model gives us a new way to look at the universe, quantum field theory, the theory that explains the subatomic world, doesn't address this fractal structure. So how can we bridge this gap? How can we modify the mathematical formalism of quantum field theory to incorporate the idea of a fractal universe? The key lies in the energy field. In this new model, we introduce a term in the quantum field equations that describes the fractal deformation of the energy field. This deformation depends on the fractal dimension of the energy field and the properties of the subatomic particles, like their mass, charge, and spin. To describe the interaction between the subatomic particles and the fractal energy field, we've developed new equations. These equations take into account the fractal deformation of the energy field and how it affects the behavior of subatomic particles, such as their energy levels and decay rates. But theory is nothing without evidence. So we've run numerical simulations to study the behavior of subatomic particles in a fractal energy field. These simulations validate the theoretical framework and provide insight into the dynamics of the energy field. The results: a theoretical framework that explains both the fractal pattern of the universe and the behavior of subatomic particles in a coherent way. The mathematical structure of quantum field theory is modified to account for the fractal deformation of the energy field, and new equations describe the interaction between subatomic particles and the fractal energy field. This framework not only explains the fractal pattern of the universe on large scales, but also the behavior of subatomic particles on small scales. It gives us a new perspective on the nature of the universe and the way subatomic particles interact with it. But the real breakthrough is the unifying equation. This equation, the McGinty equation combined with general relativity, incorporates elements of both quantum field theory and fractal theory. It unifies science across all scales, from the simple to more complex systems, and is supported by observational data. So what's the takeaway here? The universe, with its repeating patterns on both large and small scales, is fractal in nature. And by modifying quantum field theory to include this fractal structure, we can gain a deeper understanding of the universe and how subatomic particles interact with it. And with the unifying equation, we have a tool that bridges the gap between quantum field theory and fractal theory, bringing us one step closer to a unified theory of everything.